Test. Yeah, can you hear me? Well, okay, maybe, sorry, I don't know what happened. I think, one second, yeah, it's fine. I think the previous configuration was restored or something, so. Right, let's go to the beginning. Yeah, so thanks for the introduction. Sorry for this slight delay. So yeah, I'm going to talk about higher categories. Before I talk about higher categories, I think we have already talked a lot about type theory, but that's the setting in which our work takes place in. So all I'm going to do will be internal to some Martin Löf style type theory. And yeah, I guess by now we already know that Martin Löf type theory, well, there are some proof assistants and programming languages which implement this. And we have implemented all the stuff that I'm going to talk about in Agda. And yeah, so I'm not so much interested in programming, but I'm more interested in using type theory for proving and also using it as a foundation. So if you just start with type theory, you can build build all kinds of mathematics on top of it. And in this talk, I want to talk about how to implement categories in type theory. So to be a bit more precise, we do homotopy type theory, but it's really not very different. So I will use univalence, but it doesn't really play a big role for this talk. So that's not too important. But the important thing is that we don't assume unique identity proofs. So, well, if you don't know what this assumption means, then it doesn't matter because we don't use it. But well, basically, unique identity proofs would mean that if you have some equality type, like this one, then a priori, well, without the assumption, we don't know how this type looked like. It could be very complicated. With this assumption, the assumption would make sure that there could only be one such proof of equality in this type. But well, we don't make this assumption. And yeah, so this is important in homotopy type theory, where you have this principle that an equivalence between two types can give rise to an equality between these types. And then, of course, if you have two different equivalences between the two different types, you could have two different equalities, and so on. Okay, let's get started. So why is it actually hard to define categories? It's actually kind of straightforward to write down a definition which looks correct, right? So we can say a category has a type of objects and a family of morphisms, which is indexed twice over the objects, and then some composition operator and some associativity equality. And yeah, then we also need some identity and equations that ensure that the identity behaves correctly. Okay, but now I'm telling you that this whole talk is about defining categories, so it cannot be that simple. Yeah, I think so. So the thing is that, well, of course you can give a definition, but a definition on its own is not wrong or right, but a definition on its own is also not very useful. It's only useful if you can prove theorems about this and do constructions with it and so on. And what I'm saying is that if you use this simple definition here, then some very basic constructions will fail. So for example, let's say we have such a category and we have an object X, and let's try to define the slice category, C slice X. So the slice category, well, as objects, it has morphisms into X, like here. And morphism between F and G is a morphism H in the original category, together with a proof that this diagram commutes. And now what we can see is that you always already need two pieces of data to define only one single piece of data. So to define objects, you already need objects and morphisms from the original category. And to define morphisms, we need morphisms, but also composition from the original category. And now I'm out of space, so I'm not going to do it. But it's well, hopefully believable that if you try to define composition in the slice category, then you already will need to use that the original category was associative. And now, if you want to prove associativity for the slice category, it turns out that actually you cannot do it because, well, there's just no datum here which would help you. So what you need is that this associativity equality somehow is coherent. And yeah, if you look at it, it's actually not so surprising that what you need is this usual pentagon equality, right? This this is familiar from the theory of bicategories. I have it again on the next slide. So this pentagon would just say that if you have four morphisms like this, I omit the circles just for saving space, and they are just associated in one way, and you want to change and move all the brackets to the right, like this. Then there are two canonical ways how you can do this. Like either you can first shift this outer bracket, and then you shift the inner bracket, or you just first shift the inner bracket and then shift the outer bracket and then shift the inner bracket again. And these are all applications of the associator. And now we need this to commute. So we need some equality, which gives us this pentagon. And yeah, so the thing is, a priori, we haven't put this pentagon into our definition of a category. So there's nothing we can do. And now the naive solution would be, okay, let's just take the definition of a category and just add this pentagon equality. And yeah, so that's great, because now we can, for the slice category, we can really prove associativity. But the problem is that now we would also want to prove that the slice category is a category which now has this pentagon. So we would like to derive this pentagon equation, which now unfortunately we again cannot do. And in order to do this, we would need the next coherence datum, which is this Stashev polytope K5. And yeah, so we could go on like this, but I think at this point it's already quite plausible that this will take a long time. So the basic reason is that we know that types carry the structure of infinity categories. And so, yeah, basically, if you try to treat them as ordinary categories, which have strict equality laws, then yeah, you won't be able to capture all of them. So the natural notion of categories in homotopy type theory is really that of a higher category, right? So the question is, how can we define higher categories in homotopy type theory? That's basically the question of our paper. So I want to make a side remark that it is actually possible to do ordinary categories in homotopy type theory. This was done by Ahrens, Capriotti, and Schulman. And so there you just take categories and you add this axiom that the morphisms satisfy UIP. And these are well behaved, and you can do a lot of normal category theory, but also they don't capture many examples. So for example, take the universe of types and functions. This should be a category, right? But unfortunately, if you make this restriction, it's not a category. Yeah. So our goal is to find some more general definition of higher categories which capture more naturally occurring examples in type theory. Right. So the end product of our paper is a potential definition for higher categories, and we call them complete Semi-Segal types. This is because, well, what we actually do is we just look through the literature and find some ideas from very clever people, and we just put them together and check that it really works in type theory. And it turns out it works very nicely in type theory. So yeah, the first ingredient of this definition are semi-simplicial types. This is something which has been discussed a lot in the community for homotopy type theory, and they give the raw data. The second thing which we need to put in is the Segal condition, which Charles Resk has proposed 17 years ago or so. And this was in a very different context, right? These were Segal spaces and outside of type theory, but we can just translate exactly the same thing into type theory and observe that it works pretty well. And the Segal condition gives us coherent composition. So by coherent composition, I mean composition together with associativity, together with the pentagon law, together with the associator for the pentagon, and so on. So then the last thing which we need is, well, we need to find a way to put identities in, because so far we only have higher semi-categories. And identities are a bit of a problem in type theory because usually what serves as identities are these degeneracies in simplicial sets, if you know about these approaches. And in type theory, we only can do these semi-simplicial types. But fortunately, there is a very clever, nearly trivial, but also ingenious trick, which is due to Lurie and Harpaz, which makes it very simple to define an identity structure. And even better, this identity structure will turn out to be univalent. So this is another property which you would want of a category in homotopy type theory, at least most of the time. It basically means that different notions of sameness on objects coincide. So like isomorphism of objects and equality of objects coincides. So there's no risk of confusion, and these categories are pretty well behaved. And now, yeah, again, as before, giving a definition alone is not really useful. We need to be able to do something with this definition, or at least have some piece of evidence which tells us that this definition makes any sense. And the main work of this paper is to check that for low numbers n, this general definition of n categories matches with the definition of n categories which you can do by hand. So for example, for n equals 1, yeah, you get normal ordinary categories. So we can compare, we can compare our definition for n equals 1 with the ordinary categories of Ahrens, Kapulke, and Schulman. And yeah, it turns out they are indeed equivalent. And yeah, we have done this in Agda, and we have also done this for n equals 2, which was quite a lot of work, but also worked in the end. And yeah, okay. So in the rest of the talk, how much time do I have, Thorsten? Okay, so in the remaining 5 minutes, I will go very quickly through these 3 components here to explain what they are. Right, so semi-simplicial types. Semi-simplicial type has components which are points. This is a type A0 of points, and I just draw some points here to illustrate this. Then for any pair of 2 points, we have a type of lines or edges, which I call A1. And so I draw some of them here. And now in the next stage, whenever we have some triangle, we have a type of fillers of this triangle. I call this A2, right? And now it's pretty clear how you would continue doing this. So it's clear that for A3, you would look for boundaries of tetrahedra, and then A3 would give you families fillers for such empty tetrahedra and so on. So it becomes increasingly difficult to write this down and even more difficult to draw it, but it works. And yeah, so now what do these semi-simplicial types have to do with categories? So this, I hope, is not too difficult to see if we start. So category has these objects and morphisms, and now if we look for semi-simplicial types, these are exactly the same, right? We first have a type of lines, and then a type of points, and then a type of lines. So, but now the next bit is a bit different, because the composition operator gives us, yeah, for something from B to C and something from A to B, it gives us something from A to C. But for semi-simplicial types, it's a bit different, because there it gives us a family of types indexed over these edges from A to C. But I'm now saying that if we just add a small thing to semi-simplicial types, then these two things are again equivalent. And what we need is this general property that having an element of a type X is just as good as having a type family over X, which has the property that there is exactly one element in X where this family is inhabited. So is contra stands for is contractible, and this means that there's exactly one such element. Yeah, so right. So now we just need to, so now what we need for H2 is this red thing here. So we can just unfold what it means here, and it looks like this. So it's admittedly it's already quite long, but conceptually it's quite clear. So for all G and F, we have exactly one H as an edge from A to C, so that this triangle FGH has a filler. And yeah, if we draw this situation, then it hopefully becomes clear what this means. So it says that whenever we have such a configuration of an edge F and an edge G, we call this a horn. Then the type of possible fillers is contractible. So there's a unique such edge H together with a filler for the triangle. So right, this gives us composition. Right, and in general, we can do this on all levels, not only in 2 dimensions. So this is this is one possible formulation of the Segal condition in type theory. There are many equivalent ways of formulating the Segal condition, but this is the one that we have chosen. And it just says that whenever you have such a horn, there is exactly one filler. So in 2 dimensions, we have already seen this. In 3 dimensions, it would look like this. So we have some tetrahedron where one face is missing. I hope my drawing makes any sense to you. And yeah, in this case, we can find this missing face together with something inside, which I cannot draw. And now, yeah, for k equals 2, we have already seen that this gives us composition. And for k equals 3, well, you can check that it gives you exactly associativity. And for k equals 4, which I really cannot draw anymore, but for k equals 4, this condition that you can fill such horn gives you exactly the pentagon equality. Okay, I think I've already emphasized that what we do is really only translating this to type theory and checking that it works really nicely in type theory, but the basic connection between horn fillers and composition structures is, of course, quite well known in mathematics. Right. Okay, so now, finally, after we have this composition structure, we want identities. And yeah, as I already said, we use some strategy or some very simple trick, which is by Lurie and Harpaz. And so it works by just saying that, well, some edges are special because some edges, which I call E here, have this property that you can compose in the wrong direction, right? If you have a horn like this, it looks like it shouldn't be possible to compose because they are not consecutive morphisms. But we say that E is a neutral morphism or just an equivalence if such horns still have unique fillers. And now we just say that a semi-simplicial type is complete if every point has exactly one outgoing such neutral edge. So this basically says that we have exactly the right amount of equivalences. And when we do this, then it's easy to construct identities. Because if we want to get an identity on X, then we just take this unique equivalence that we get, write it down twice, and we use the property of this equivalence, and we get some identity X, identity on X like this here. Okay. Yeah, so I'm nearly done. I think my time is also nearly up. So in conclusion, for this notion of a higher univalent category, which we call complete semi-Segal type, we need a semi-simplicial type restricted to n+2 components if we want an n category, and we want to equip it with the Segal condition, with completeness, and in order to make up for this fact that we just stop at a certain level, we just truncate so that the highest level becomes trivial. And the nice thing is that all these three pieces of data here are propositions in the sense of homotopy type theory, so they are well behaved on their own and don't need further coherences. Okay, so now after we have this definition, we would want to do something with it, but most of what we want to do with it is still work in progress. So for example, we could try to define some higher categorical model of type theory in type theory, or we could try to use it to construct some higher inductive types and so on. Yeah, okay, many thanks.
This is nice. Your initial example about the slice categories, how does it apply here when you actually truncate?
Yeah, so when you truncate, then the last datum which you would need for the slice category becomes trivial. So it's like for ordinary categories, you have this, I mean, let's say not in type theory, but like in standard mathematics, this associativity is just some equality. It's not data, but it's a law. And this law doesn't need any additional coherences. So, I mean, it's like the difference between ordinary categories and bicategories is that the associator for bicategories is a datum, and it needs to be coherent to be well behaved. And here, if we truncate, then this means that we go down. So from infinity categories, we go down to n categories, and we can even truncate on a very low level, and then we will go down to ordinary categories, where these associators just fulfill all possible coherences which you could imagine.
Sorry, what does this look like if you use cubes rather than simplices? Is it any better or worse?
Yeah, good question. So, well, I mean, this battle between simplices and cubes is quite exciting, and it's hard for me to see why one is actually better than the other. So one thing I found is that if you use So I think if you use cubes, then this completeness doesn't work as well. But actually, I think it could also work with cubes, but I suspect it wouldn't be as nice. But I haven't worked it out.
Can you show that n types and functions between them form n category? Did you prove it for 2 types? Or?
Yeah, right, exactly. So the standard example for ordinary categories is the universe of sets and functions. And in our case, this just generalizes. And the standard example of an n+1 category would be a universe of n types and functions between them.